Another important issue let me talk about during continuous casting, which can generate problems of entrapment at certain locations of continuous casting. I have mentioned earlier that continuous cast product is not having a uniform quality. Certain portions of the casting is relatively inferior in quality. I have mentioned at the start of casting and the end of casting, at the change of little changeover at the stage of sudden fluctuation, there is a possibility of entrapment. So, those areas are relatively inferior. Now, this will be very interesting. Look at the two molds. Continuous casting mold can be of two types. The normal type is straight mold, that means it is a vertical mold, we call it vertically straight, it is coming down, and then it has to be bent, and finally it has to be straightened to make it horizontal. Initially the mold is vertical, but the mold is continuously, it is not a vertical one, because otherwise you will have a very maybe 10-storied continuous casting shop if you have a vertical mold, which is not practical. So, normally the mold is initially vertical, and then it has to be straightened or bent or straightened, and then it becomes finally horizontal. The cast product when it is finally coming out is horizontal, but initially the mold is vertical. Now, you see here it is totally vertical, here it is not vertical, it is a curved mold, you just see there is a curved mold. So, then it has to be straightened, curved mold only straightening is necessary to make it horizontal. But if you have a totally vertical mold, then what happens? First it has to be bent, then it has to be straightened. So, there is a bending, there is a straightening. All these arrows indicate that when you are doing straightening or bending of the mold, so you see what is there inside the mold. This is the mold, outside the mold it is the strand, this is basically the strand, this is the mold, then below the mold the strand is coming out. So, here is a curved mold and then the strand will come out. So, if the strand is being straightened or strand is being bent and straightened, so lot of stresses are getting generated at this inner surface, at the outer surface. Now, one thing you must remember, look at the curvature of the mold. This is called the inner radius of the mold, this one, and this is called the outer radius of the mold. This is the inner radius of the mold, this is the outer radius of the mold. So, the stresses on the shell, something will be at certain locations, it may be something at the opposite outer radius, it may be something else. It may be tensile here, it may be compressive, it is tensile here, it is compressive here, here it is compressive, it is tensile. So, these aspects I will discuss later on when we come to the continuous cast quality, whether there will be cracks and all, but right now try to understand what is happening. I have mentioned that there is a possibility of some inclusions getting generated or entrapped in liquid steel, which will try to float up in the mold. Now, when inclusions are floating up, what is happening? If you have a straight mold, inclusion will straight away will float up like this and get absorbed at the top of the mold. That means, when there is a liquid slag here at the meniscus level, it will get absorbed. But here what is going to happen? When they are floating up, there is a possibility of, because liquid shell has solid shell has already formed, there is a possibility of some inclusions getting entrapped in the solid shell which is forming during initial stage of solidification. So, here that possibility is not there because it is going vertically. Here it is also going vertically, but since the mold is curved, so there is a possibility of certain inclusions getting entrapped, getting inside the solid shell which is forming here is high in case of a curved mold. So, in a situation where we have a curved mold, the uniformity of in the cast product, uniformity of inclusions in the cast product will not be there. certain portion near the inner radius we will have more inclusions, we will have less quality, inferior quality these areas. But if you have a vertical mold, that possibility is not there, it will be relatively uniform, whatever inclusions are there will be relatively uniformly getting absorbed in the solid shell. But here certain areas of the solid shell near the inner radius, this is the inner radius, there is a possibility of getting more inclusions near the inner radius. Now, so from the quality point of view, vertical mold is better, this curved mold is not good, is undesirable. But from the point of view of which I will be discussing later on, from the point of view of having internal stress in the solid shell, you see curved mold is better because you only have to do straightening of the shell. Here for a vertical mold you have to first do bending and then straightening, that means you are having some additional stresses on the shell. During bending some stresses, again during straightening some stresses. But for a vertical, this is for a vertical mold. For a curved mold, where this situation there is only straightening, because no bending is necessary. Already the mold, because of its curvature, it is already getting bent when it is coming out of the mold. The shell is already bent. So only straightening of the shell, straightening of the strand is necessary. So the amount of stress generation is relatively less for a curved mold compared to a vertical mold. But as I have mentioned, straight mold is better from the point of view of inclusion entrapment, because uniformly whatever inclusions will be there, the quality will be relatively uniform. But here relatively more inclusions, when they are floating up, they are trying to get absorbed in the solidified shell here. So near the this portion is called inner radius of the mold, near the inner radius of the shell you have more inclusions. This we have found out by analyzing the cast product. You just look at relatively uniform distribution of NMI along slab thickness for straight vertical mold. So I am talking of a situation here, the mold is vertical, so whatever slab is forming, finally the slab is coming like this. So we have tried to analyze what is the distribution of the inclusions from inner radius to the outer radius, from top surface to the bottom surface. The inner radius will finally generate the top surface, the outer radius will finally giving you the bottom surface. Here the inner radius again is giving the top surface, but the possibility of inner radius, near the inner radius, the more inclusions will be there in case of curved mold. So we have found out this by analyzing a liquid, how the liquid steel when it is getting solidified at as a slab. So what is the distribution of inclusion? So I am talking of a slab having 200 millimeter thickness. So we have measured total oxygen. Total oxygen is what? Is a measure of oxide cleanliness. I have mentioned several times in this course that total oxygen is a summation of dissolved oxygen and oxygen presence as oxide inclusions. If the steel is killed, properly killed, total dissolved oxygen will be around say 5 ppm max. So if you have a total oxygen of say 30 ppm or 25 ppm, so the remaining amount will be oxygen present as oxide inclusions. So total oxygen measure these days, nowadays, is being done for measuring, getting an idea of oxide cleanliness in steel in the final product. So we have in the slab at a distance of say 25 millimeter from the surface, initially at the surface, then 25 millimeter, every 25 millimeter we have taken samples and analyzed total oxygen. How we measure total oxygen, this I have discussed earlier. So, for a straight mold we find that the distribution of total oxygen, that means the distribution of oxide inclusions is not that bad, is more or less uniform towards the thickness of the slab. This is say top portion, if it is the top portion, this is the bottom portion. If this is the inner radius, this is the outer radius of the slab. Now, look at a carved mold situation. You find the same 200 millimeter slab, but the slab has been cast in a carved mold, unlike in the earlier situation where it was a vertical mold. So, in a carved mold, again total oxygen we have measured, we find that at 1/6 of the slab thickness, say 200 millimeters, somewhere here, the total inclusion level is quite high. This is the inner surface near the inner radius. So, this area inclusion, mode of inclusions, that is why mode of oxide inclusions, so that is why the total oxygen is more compared to the other portion of the thickness. So, is it clear that if you have a carved mold, there is a possibility of having more inclusions near the inner radius, as I have mentioned here, relatively higher distribution of NMI, non-metallic inclusion, at about 1/6 of the slab thickness of carved mold. Unlike a situation for a straight mold, it is more or less uniform, there is hardly much of difference. Whatever difference is there, maybe it is an experimental error, but here you find it cannot be an experimental error, it is around say almost 40, 35, 40, and here it is around 20, maximum 25. So, this cannot be an experimental error. That means, near the inner radius inclusions are more entrapped, getting entrapped much more. So, there is a possibility of poor cleanliness at this portion. So, whenever this slab you will be rolling, so one surface from the, if you have not toppled the slab during rolling, that means the bottom surface will be having more defects, otherwise the top surface, that means the inner surface. So, it is better to mention the inner radius, surface at the inner radius will have more defect. So, whenever you are rolling that slab, so this surface which is at the inner radius will have more defects. More defects will be exposed when you are doing hot rolling or finally cold rolling at this for these slabs. So, what I have told is not only certain slabs which have been cast, I have mentioned, if I go back, not only slabs or blooms or billets which have been cast from the start or end of cast area, they are relatively bad, I have mentioned. The sudden change in meniscus level, if it takes place at a sudden change in speed during casting, that particular location will be bad, relatively inferior, more inclusions are expected. So, start or end of casting, just after lateral changeover, sudden fluctuation if it takes place during casting, these areas are relatively inferior. So, these products, portion of the cast, whether slab, bloom or billet, they are relatively inferior. Now, I have talked about also another important thing, that not only those portions will be bad, but even in the thickness of the slab or bloom or billet, the surface which is near the inner radius, this portion, this is inner radius. If you have a straight mold, inner radius and outer radius, more or less the distribution is more or less similar. But if you have a carved mold, near inner radius, you have relatively more inclusions compared to the outer radius. So, if you analyze the slab from this surface to the other surface, from the inner radius to the outer radius, we will find inner radius will have relatively more inclusions, outer radius will have relatively less inclusions. In straight mold, it is more or less uniformly distributed. That is what I have shown, you see, this more or less uniformly distributed. So, this is important, how we have seen, how we have analyzed, we have drilled samples. So, it is a 200 millimeter thick slab. So, from the surface we have drilled, then we have gone into say 25 millimeter, again we have drilled to get the sample, we have drilled another 25 millimeter and taken sample. So, throughout the thickness we wanted to see what was the distribution of cleanliness, what is the distribution of non-metallic inclusions. So, total oxygen gave an indication that for a straight vertical mold throughout the thickness from the inner radius, this is the inner radius area, this is the outer radius area, from the inner radius to the outer radius more or less uniformly distributed inclusions. Inclusions will be there. I have mentioned earlier that no steel is free from inclusions. There will be inclusions. Our job is to control the level of inclusions. Our job is to see that inclusions are within the desirable extent. The volume of inclusion, the amount of inclusion, as well as the size of inclusions are within control, within level, within desirable levels. So, we have found that this is more or less uniform. Total oxygen level is around 25, say 25 ppm, which is not bad, which is relatively reasonably good. But here you see certain areas we are having more inclusions. That means, when you are going to process this slab, it has been found that the surface which is near the inner radius, they will have more defects. More surface defects will be generated here, because it is about 35 to 40, which is very high compared to a level of say 20. So, the inclusion average inclusion level for both the cases are more or less same, you will find. But here what is happening? One particular surface, near one particular surface, the inner radius surface, it is more, in the other area it is relatively clean. Average may be same for both the cases. So, here when we are rolling the material, the slab, one surface will expose more defects, more surface laminations. So, we will be getting more defects in this particular slab which has been cast from a carved mold. So, it is, we should not get surprised with these results, because it is expected. It is expected that when you have a carved mold, there is a possibility of some inclusions getting more entrapped. Here inclusions getting more or less uniformly entrapped, because the solid surface is increasing this way. So, there is a possibility of here when they are floating, they are trying to get absorbed, more inclusions are getting absorbed at these locations. But here they are floating and getting absorbed uniformly throughout the surface. So, this is the difference between a straight mold cast and a carved mold cast. So, in both the cases, if the inclusions are more or less uniform, we will have relatively more inclusions near the inner radius than at the outer radius. But for a straight mold, it is uniform. So, even if the level of inclusions, level of cleanliness are same in both the cases, the distribution are not same. Distribution of inclusions are more for a carved mold and less, or rather uniform. Distribution means more inclusions near the inner radius, but here it is more or less uniform, more or less uniform throughout the thickness. I am talking about the thickness of the slab here. I have taken samples at different thickness levels by drilling and then analyzing the total oxygen, assuming that the dissolved oxygen is relatively less, because in both the cases it was a aluminum killed steel. So, the dissolved oxygen will be less than 5 ppm, within 5 ppm. So, if the level here is around 30 or 25, so the rest, the remaining oxygen is present as oxide inclusions, as oxides. So, total oxygen is giving an indication of the oxide cleanliness. In both the cases, the average level of cleanliness is more or less same, but here certain area near the inner radius is having more inclusions. This is very interesting. So, when we process this material, we will find more defects near the surface which is at inner radius, which corresponds to the inner radius, and the surface which corresponds to the outer radius are relatively more clean. So, we will have more defects at one surface and less defects at the other surface, but for a straight mold defects are more or less uniform. That means whatever incidence of defects are there, it is more or less uniform at both the surfaces. And another interesting observation is that, which is from common sense you can make out, that whatever defects are there in the slab, cast slab or cast bloom or cast billet, when you are processing it, the more you are processing, there is a more possibility of defects coming to the surface, is it not? Because the surface area is increasing. So, whatever defects were there inside the cast slab, so as you are rolling it, rolling means this 200 millimeter thickness will become, when you are hot rolling it, this 200 millimeter will become maybe 5 millimeter or 6 millimeter or maybe 4 millimeter. So, whatever defects are there distributed in the whole bulk of the cast slab, they will try to come to the surface because the surface area is increasing. So, the more you roll, more defects get exposed to the surface. So, if you have a good inspection facility, then you can find out at what stage these defects are coming out and what is the distribution of the defects, like whether defects are coming more on one surface or are coming near both the surfaces. If you roll a slab, this slab if you roll, we will find that defects are coming more on the surface which correspond to the inner radius of the caster. The other surface which corresponds to the outer radius will have relatively less defects. This has more defects. Here more or less when you are trying to roll it to lower and lower thicknesses, defects will be there, defects will be getting exposed uniformly at both the surfaces. So, I have tried to mention that what are the possibilities of entrapment distribution, not only along the length of the casting, but also along the thickness of the casting. If the length of the casting I have mentioned, basically the distribution is because of the at the start or end of the casting, that is when there is a non-steady state, there is a possibility of getting more entrapments. Little changeover, again non-steady situation you can get, sudden change in meniscus level or speed, non-steady. So, whenever there is a non-steady state of casting situation, there is a possibility of more defects. This is with respect to the length of the cast product. At certain location of the length you have more defects. So, you know what are those locations, whichever location corresponds to the start or end of casting or little changeover, during the casting process, or whenever there is a sudden change in meniscus level of speed, So, those locations you identify when the casting is over, and those portions of the length of casting you try to keep it separately, because it is expected that those portions of the casting will have inferior quality. But what I have mentioned here is not only the length of the casting, even the thickness of the casting, there is a possibility of some distribution of inclusion. It is not uniform, it may not be uniform. If you have a vertical caster, it is going to be uniform, the thickness is going to be uniform quality, have of uniform quality, but for a carved mold the thickness will have non-uniformity. So, that the surface which corresponds to the inner radius will have more defects, the surface which corresponds to the outer radius will have less defects. So, till now I have tried to cover what are the possibilities of entrapments in liquid steel, how they are getting entrapped, in which way you can control the entrapments, we can control their size at different stages of secondary refining, that means when liquid steel is in ladle. So, ladle slag is very important, ladle refractory is important, so that you do not get more entrapments. The process is very important. How do you do? You do first deoxidation, because that is very important, because when you are just tapping liquid steel from BOF from the primary level like BOF or EAF, you have maybe 500 ppm oxygen. So, the dissolved oxygen is very high. No steel, no good quality steel should have so much of dissolved oxygen. You cannot even cast that steel, because what will happen to the liquids, what will happen to the dissolved oxygen? It will come out as blowholes and pinholes. It will be like a strainer, lot of holes in the product, even the cast product. So, it is useless. So, the first thing is deoxidation. The first thing of improvement of quality of liquid steel is deoxidation. If you do a good deoxidation, your liquid soluble oxygen will come down to less than 5 ppm. That means aluminum deoxidation, it will come down to less than 5 ppm. Then there is desulfurization, because what I have mentioned when I talked about the inclusions at the beginning of the course, that the inclusions basically are either sulfides or oxides or complex oxysulfides. So, by deoxidation you are bringing down the oxygen level, by desulfurization you are bringing down the sulfide inclusion level. Then you can do, to take care of nitrogen and hydrogen, you can do degassing. So, these are all secondary refining techniques. Then from the casting point of view, I have mentioned what are the precautions we have to take at the when liquid steel is coming down from ladle to tundish, and from tundish to mold. So, what are the precautions in ladle, what are the precautions in tundish, what are the precautions in mold, so that you get a relatively less entrapment, relatively good quality of steel, relatively less oxides inclusions and sulfides inclusions. We do not want large exogenous entrapments. Exogenous entrapments, I have also mentioned what are the possible exogenous entrapments. Yeah, complex, these are mostly, you find out mostly oxide type of entrapments, aluminum oxide with some silicon or manganese oxides, or slags, calcium, silicon, aluminum oxides. It might have some sodium oxides also if you had a mold slag, some fluoride also, calcium fluoride is added as fluidizer in mold slag. So, and you can know also by analysis, analyzing the defect samples, that also I have mentioned. Like if you have a defect, just under the defect whether any entrapment is there, whether any exogenous entrapment is present. Such large defects, there is a possibility of having some entrapment. So, we should know what are where from the entrapment is coming. So, what are the sources of entrapments, what are the genesis of entrapments. So, this is possible by cutting a small sample without destroying the sample. We put it under scanning electron microscope which has ADX or WDX. So, we know from the elements present what are the possible sources. So, if you know the sources, we know what went wrong. This is of course post-mortem. So, we have to take care subsequently, that means in subsequent stages, if you know what are the possibilities of defects from the knowledge of steel making, knowledge of secondary refining, knowledge of continuous casting, we know what are the possibilities of defects, what defects can get inside liquid steel and they get inside the cast product, what will be their distribution. If you know that, we have to be careful. I think in this process we can control the entrapments, we can control the amount of entrapments, we can control the size of the entrapment. Both are deleterious for the quality of steel. One is the amount of entrapments, that means volume of entrapments, another is the size of entrapments. Both will have undesirable effects on the steel quality. So, both have to be controlled. Thank you very much.